So this problem is about solving for a reactant using a chemical equation. So it looks like we're going to be given a written description of a chemical reaction, which will have to turn into a balanced chemical equation. So it says a major component of gasoline is octane. When octane is burned in air, it chemically reacts with oxygen gas. So what they're really describing is a reaction occurring between octane, which is one of the reactants, and O2 in the air, which is the other reactant. And so then that's going to make some products, and that's what it tells us is being made next. It says to produce carbon dioxide and water. So CO2 and water vapor. There we go. So what we have to do now is, in order to be able to use this equation to do anything, is to balance it. So to balance it means that we're going to make sure that we have the same number of atoms on both sides of our arrow. So I'm going to begin with carbon. I've got 8 carbon atoms on the left, and I've only got the 1 on the right. So I need to get that guy up to 8. And then I'm going to move on to hydrogen, and I've got 18 on the left, and I've got 2 on the right. So I need to get that up to 18, and I'm going to do that by multiplying it by 9. And then now I've got oxygen, and oxygen is often tricky. So I've got 2 on the left, and then on the right I've got 8 times 2, that's 16, plus another 9, that is 25. So now my oxygens come as oxygen molecules, so I can only add 2 at a time. So I'm going to have to add or multiply this guy by 25 on 2. Now, when we write balanced chemical equations, by convention, we don't use fractions for any of our coefficients. So what I'm going to do here is I'm going to multiply everything by 2. So I'm going to end up with 2 of those, 25 of those, 16 of those, and 18 waters. And now everything balances and I don't have any fractional coefficients. So now it says what mass of oxygen gas is consumed by the reaction of 7.8 grams of octane. So mass has units of grams, most commonly in the SI system. So what we're going to do is we're going to say we've got 7.8 grams of that, and we have to figure out how many grams of O2 we've got. So this is what we call a grams of A to a grams of B problem. And so what I'm going to do is I'm going to take my grams of thing A, and I'm going to multiply that by 1 on its molar mass, and that will give me the moles of A. And then what I will do is I'll multiply this by my mole ratio, which is why we needed that balanced equation, which is the moles of my thing B by my moles of my thing A, and it's always the B's what we're trying to convert into. We're not done because we want to end up with mass, not moles. And finally what I've got to do is multiply by the molar mass of my thing B. So whenever we're doing a grams to grams conversion, it always goes like this. I'm going to take the grams of A, multiply it by 1 on its molar mass, multiply it by the moles of B over the moles of A, and these numbers are just going to come from our balanced equation, and then finally I'm going to multiply it by my molar mass of B. And so what will happen is these conversions, it'll go from grams of A to moles of A to moles of B to grams of B. And we always do that, and each of these conversions requires a conversion factor. So you see every time we have 1, 2, 3 conversion factors whenever we do that conversion. All right, and they're always the same thing. It's always 1 on the molar mass of A times by the mole ratio times by the molar mass of B. So what I'm going to do now is I'm going to need the molar masses of my two components, so my B and my A. So let's see if we can get that. So the molar mass of my octane and I'm going to need the molar mass of my O2, which will be grams of O2 for every 1 mole of O2. And how I like to get these guys is by using a molar mass calculator. So I have one in my bookmarks here. I'll put that in. So it was C8H18. There we go, 114.23. And then this one is 32.00. Okay. Just double check that just to make sure. There you go, 32.00. Okay, so now we're going to go ahead and do our math, and we'll cancel our units out as we go across. So 7.8 grams of octane, and we get 1 mole of octane for every 114.23 grams of octane. According to our balanced equation, we get 25 mole of O2 for every 2 mole of octane. And then finally, there are 32 grams of O2 for every 1 mole of O2. So what does that mean? Grams of octane cancels, moles of octane cancels, moles of O2 cancels, and it leaves grams of O2. Now we were asked to round to 2 significant figures, so we'll make sure we do that once we've got everything worked out. So it was, my calculator on, 7.8 times 1 on 114.23 times 25 on 2 times 32. And then we're going to round that to 2 significant figures. So to 2 significant figures that we have to decide, is it 27 or is it 28? And it's closer to 27, so it's going to be 27 grams of O2. And so there you go. And that's it. So you need quite a lot of oxygen to consume that 7.8 grams of octane. So that's just what we call a grams of A to grams of B, and they're always done the same way. You take your grams of A, multiply it by 1 on the molar mass of A, multiply it by your mole ratio, so your moles of B for every mole of A, and then finally you multiply it by your molar mass of your whatever your B is. And they're always done the same. You just take that starting number and multiply it by those 3 conversion factors. You can't get your mole ratio without a balanced equation, and then you will need to calculate those some way or another. You can either use a website, or you can calculate them by adding up the masses of the different atoms that are present in the formula for the compound. Okay, so hopefully that helps explain that kind of problem. So let's have a look at the last objective. This one is solving moles to moles limiting reactant problems. So again, it looks like we're given a written description of an equation, and we're going to have to decide what are the reactants, what are the products, and then we're also going to have to balance that equation. So it says solid aluminum and chlorine gas react to form. So these are the two things that are reacting, aluminum and chlorine, to form solid aluminum chloride. So that's the product, AlCl3. So perhaps already you can see that it doesn't balance because we have different amounts of chlorine on either side of our arrow. So the aluminums, we've got one on the left and one on the right. But the chlorines, we've got two on the left and we've got three on the right. So how can we get those to balance? Well, if I multiply this guy by 3 and then this guy by 2, I would have 6 chlorines on either side. The only problem now is that my aluminums don't balance. So I have to put a 2 out there to get that to balance. And now I have a balanced equation where I only have whole number coefficients. So that's not too bad. We've got that. Now it says we're going to put 5 moles of aluminum in our reactor and 1 mole of chlorine in our reactor. So the question is, could half the aluminum react? So 5 on 2, half of the aluminum would be 2.5 moles of aluminum. So how much chlorine would we need in order to react that amount? Well, according to our balanced equation, we have 3 moles of chlorine is used up for every 2 moles of aluminum. So in order to react 2.5 moles of aluminum, I would need, let's just do this, 2.5 times 3 on 2. You can see that I would need 3.75 moles of chlorine. And I don't have 3.75 moles of chlorine, I've only got the 1. So what will happen is the aluminum will keep reacting until I've used up that 1 mole of chlorine, and then it will stop. So it's really telling me that the chlorine is going to run out before I run out of aluminum. The chlorine is what we call the limiting reactant. Now in this case we don't need to do anything else. It says if you answered yes, calculate how many moles of aluminum chloride would be produced. We don't need to do that step because we answered no. So let's do another one. It says methane and oxygen gas react. So these are going to be our reactants. And then it says to form, so what comes next are going to be our products, carbon dioxide and water vapor. So we know that we need to balance. So we have 1 carbon on the left and we have 1 carbon on the right, so carbon is balanced. Move on to our next element. We have 4 hydrogens on the left, but we have only 2 on the right. So I'm going to multiply everything by 2. Now hydrogen is balanced. Now oxygen is always a little awkward. We have 2 oxygens on the left, and we have 2 plus another 2. We have 4 oxygens on the right. So this is a little easier. I just need 2 of those, and now everything balances. So what I'm going to do now is start work on the math. It says suppose you have 11 mole of methane, 11 mole of that, and 3 moles of O2. Then it says, what would be the limiting reactant? Which is really saying what one would run out first. And so there's a very simple way of doing this is to recall that the limiting reactant is the one that produces the smallest yield of product. So let's consider how much CO2 would be consumed if I used up all of my O2 or all of my methane, and whatever gives the smallest yield is the limiting reactant. So I got 11 mole of methane, and according to my balanced equation, I get 1 mole of CO2 for every 1 mole of methane. And so if I used up all of my methane, I'd get 11 moles of CO2. Now, the only reason that I'd be able to use up all my methane is because I had enough oxygen to react with it. So how much oxygen have I got? Well, I've got 3 moles of O2. So 3 moles of O2, and my balanced equation says I get 1 mole of CO2 for every 2 moles of O2. So moles of O2 cancels, and so that would mean that if I used up all of my oxygen, I could make a total of 1.5 mole of CO2. So what this is telling me is that that is the maximum amount of CO2 I can make, because then I run out of oxygen. So what is the limiting reactant? The limiting reactant has to be the O2. It is the one that runs out first. It is also the one that produces the smallest yield of product. So it's not too bad. We just had to use the mole ratio to identify the limiting reactant. Now, it is important to realize that we couldn't go through that process until we had a balanced chemical equation, because we need the balanced chemical equation to get these mole ratios that we're going to use in the calculation. All right, hope you found that helpful. Good luck with everything.